Okay, let's go.
Well, thank you. First of all, let me thank the organizers for giving me this wonderful opportunity. And it's really nice to have a complete session on Hafnia. Last time I was speaking, I was the only speaker about speaking about Hafnia, and this time it's a very nice topic that has excited many people here. And I also want to thank Ron here for, in fact, giving a very comprehensive introduction of these Hafnia ferroelectric materials. Today I will be speaking about ferroic ordering through nanoscopic confinement, which goes back to the question that was asked at the end to Ron about these compressive pressures because of nanoscopic confinement in Hafnia zirconia thin films. This is majorly a work that is published in Nature Materials very recently, and if time permits, I will also show you some of our recent results on trying to grow these thin films epitaxially on directly silicon. Okay, this is a collaboration between University of Groningen, the Beatrice Noida group there, University Paris-Saclay, Santhal Supelek, so many names there, where Brahim and Sylvia participated, and also from Luxembourg Institute of Science and Technology with Jorge and Ajay doing calculations for us. Next.
Is it black? Is it black?
No.
It's not black. Oh. This is. Can you copy the talk? There is another port? Oh, forgot. You didn't plug there. Can we remove this one? Can we remove this?
Yes. Sorry.
That should pick up that.
Okay, fine. Alright, sorry for the second technical interruption. Okay, so first of all, why study Hafnia with ferroelectrics? I would like to motivate this crowd, which actually needs no motivation, but with the context of silicon-compatible ferroelectrics on CMOS. So we have electronic devices with a lot of billions of transistors in them. Ideally, these transistors should operate between an off state and an on state with almost no current in the off state and a sharp switching to an on state. Right? But ideality is not reality. In reality, we have MOSFETs which kind of leisurely go from an off state to on state. And the leisureness of this going from an off state to on state is what is characterized by the subthreshold swing, which is the inverse of the slope, which is given by this expression. And this means that below the threshold voltage, which is the off state of the transistor, the MOSFETs actually have some finite leakage current. And this leakage current, as you keep reducing the gate length of your transistors, as you keep miniaturizing them, the problem with this vampire power or the subthreshold leakage keeps getting more and more enhanced. So we need a solution for this, and solution luckily is provided when you make one of the solutions is make the gate oxide capacitance negative, and thus comes the idea of negative capacitance.
Is my computer giving you trouble?
Yes.
It works this here. 1, 2. Yeah. That's alright. It's not going up there. You can ignore this. It's actually displaying properly. I think it's.
Okay. Okay. Yes, sir. All right. So, okay, going back to negative capacitance, we have the idea of negative capacitance, which has been published in all these papers, and most recently in this month, in fact, in these two Nature papers. And ferroelectrics are compatible with the idea of negative capacitance, and if you use a ferroelectric with the idea with negative capacitance, you can make this switching much sharper and hence reduce the problems of leakage. So this is a potential solution. So why not just go ahead using ferroelectrics on let's say FEFETs based devices. The first problem comes because of the challenge of keeping ferroic order at a nanoscale. So you have polarization which separates the charges. This creates a depolarization field which needs to be screened by using appropriate electrodes. If you don't screen it well, you have very nice, interesting structures that come because of depolarization effects, but this is not conventionally ferroelectrically switching. Right? So depolarization kills ferroelectricity, and the extent of depolarization increases as you keep reducing the film sizes. That's how nanoscale does not really sustain ferroelectricity. But apparently in 2011, the NAM lab from Germany has discovered that there is this functionality of ferroelectricity in doped hafnia-based oxides, and this is only ferroelectric in nanoscale. Okay, so this is quite contrary to our conventional understanding of ferroelectricity, and in fact they have shown that many groups ever since have shown that, that you can use several dopants, and then they show robust nanoscopic ferroelectricity. These films can be grown using various techniques, ALD, CS, chemical solution deposition, PLD-based growth techniques also, and around less than 15 to 20 nanometer sizes, all these films show this property of ferroelectricity. And since it is on hafnia-based material, it already has a proven compatibility track record with silicon, and so this is a nice material to study. Okay. With that as the motivation, I think the structure, so then we ask the question, what is the reason for ferroelectricity? Does it come intrinsically from structural aspects? For which, in fact, we have a bulk monoclinic phase of hafnia or zirconia with the 7-fold coordination. We have high temperature, high pressure tetragonal and cubic phases with 8-fold coordination, which is the commonly called the fluoride phase. And both these phases, although they are very well studied, are not polar. So the polar phase is in fact the PCA21 orthorhombic phase, and this is actually considered, this was reported in magnesia partially stabilized zirconia and also in this nanoscopic zirconia islands, much before the studies of ferroelectricity. And this is in fact considered the main reason for ferroelectricity in all these films that I showed you before that were grown using techniques that create multi-grain polyphase films. Right? Okay, but since these are multi-grain polyphase films, it's not very clear that is this the only phase that is responsible for ferroelectricity? Is it as intrinsic, or are there other extrinsic effects? For example, all these films show what is known as the wake-up effect. So in the first cycle of switching, they don't really show any significant ferroelectric switching of polarization up to polarization down. You need a certain, in this case, let's say 500 switching cycles to stabilize the polarization while switching. So this is the so-called wake-up effect. It is technologically inconvenient, and this also poses the question whether this is coming intrinsically or this is an extrinsic effect. For example, this paper, which is recently put on archive, a collaboration between again Oak Ridge and a Ukrainian group, suggests that such kind of ferroelectricity can totally be explained just based on electrochemical origins, such as oxygen vacancy accumulation and electrodes creating an elastic dipole, converting into a switchable electric dipole. Okay, so what we decided then was to actually synthesize single-phase, single-crystalline samples. Single-crystalline is too much of a stretch, but single-phase samples with the help of one technique that we know the best, which is pulse laser deposition. So here are our structures. So we have a substrate SGO. LSMO is a back electrode, and we grow a very thin layer of hafnium zirconium oxide. And we characterize this with by laying lithographically another top electrode, and voila, we see ferroelectricity. And these films are ferroelectric even in the first cycle. They don't sleep. They don't need to be woken up. Okay, so the other thing that we observe is as you keep reducing the thickness of the film, the polarization, the the value of spontaneous polarization actually increases from, let's say, 18 microcoulomb per centimeter square here to something like 34 microcoulomb per centimeter square. So this is an anomaly ferroelectricity. It keeps getting more and more robust as you reduce the thickness of the film. So this is indeed true. And going back to the wake-up, you do see that with cycling, in fact, the effects of fatigue start after 100,000 cycles, but you don't see any significant improvement of polarization or anything. So these are kind of insomnic films. They don't sleep. They are already woken up. Okay. So as to what is the reason for such a ferroelectricity, we did some structural characterization using X-ray diffraction as well as electron microscopy. And in fact, you see that in the thicker films, we do have a phase coexistence of the bulk-like monoclinic phase as well as the ferroelectric phase. As to what this phase is, I'll just come to it. And as you keep reducing the thickness of the film, you see that this out-of-plane 111 direction, out of plane 111 peak actually moves left, which suggests of some, an out-of-plane increase of D111, which is because of in-plane compression. Okay, and the same thing happens when you can make films as low as 3 nanometer thick. They still show this peak, which is which means in this case it is heavily in-plane compressively stressed. All right, so we did some pole figure analysis to see this gives us the texture of the films. So around the pole that is out of plane 111, which is this, ideally you have to find 3 poles if it is a single domain film, but we do find 12 different poles, which is suggesting that there are 4 different domains which are rotated at 90 degrees with respect to each other. So we do have multi-domain single phase films when you make these films as thin as possible. The transmission electron microscopy says the same thing about the existence of these multi-domain films. Also, it gives us an estimate of the size of these domains. The size of these domains in a 10 nanometer film is commensurate with, let's say, the thickness of the film. In a 10 nanometer film, you have 10 nanometer domain sizes. In a 5 nanometer film, you have 5 nanometer domain sizes. Okay, so as to what this phase really is it the polar orthorhombic phase that people generally talk about? We did theta to theta scans around each of these poles, and then we found that in one particular domain, let's just select this blue domain, there are 3 111 directions with a slightly lesser lattice parameter than the 4 out of plane 111 direction. So this 3:1 multiplicity is a signature of rhombohedral phase and not orthorhombic phase. So what we have is a rhombohedral phase, and transmission electron microscopy also complements this analysis by saying that the D111 is not the same as D11 minus 1, which should be the case in an orthorhombic phase. And then Jorge and H.J. helped us understand what exactly is the symmetry of this rhombohedral phase. And it turns through search for metastable structures using genetic algorithm. And then they found that there is an R3M symmetry and R3 symmetry which have certain degrees of metastability compared to the ground state of monoclinic phase. And in the R3M phase, as Ron was showing earlier, as you keep increasing the D111 or as you keep increasing the in-plane compressive strain, the polarization, the value of polarization increases. So this is quite consistent with our experimental results, except that in our experiments we do see a higher value of polarization than what is predicted theoretically. This is not normal, right? Okay, so what is the reason for stabilizing this high energy metastable state? So we have a very simple model for this, derived out of nanoparticle literature of hafnia and zirconia nanoparticles. It turns out that in the nanoparticles of interest, so if I consider a nanodomain as a nanoparticle, because of immense nanoparticle pressure, a high pressure, low volume phase such as cubic phase is stabilized just in the nanoparticle form. And to that cubic phase, if you add an epitaxial strain, epitaxial in-plane compressive strain, you extend it along the 111 direction, making stabilizing a rhombohedral phase. So again, this is a growth path. How you grow determines whether you get the rhombohedral phase or not. So this is a simple model to get this rhombohedral polar phase. All right. So this should not be there, but okay. Anyway, so is this okay, I'm almost done. So is this specific to fluoride-based systems, or because the mechanism seems quite simple. You do need to have nanoparticle pressure, and then you need to apply some kind of in-plane compressive strain. And then perhaps you can stabilize a ferroelectric phase, right? So is this specific to just fluoride-based systems, or can you see this in other systems? In fact, if you just take a look at literature, there is epsilon Fe2O3, which also shows such nanoscopic ferroelectricity. It's unclear whether these two mechanisms are same, but they smell that this could be similar. In fact, in last year in the same conference, there was a talk by Ito-san, who also showed some results of ferroelectricity on Kappa aluminum oxide type materials. Now, this one, I just removed it after hearing Professor Scott's talk, but okay. Alright, so finally, let me just give you a flavor of what we are doing now. So right now, it's all fine growing hafnium strontium titanate or all these oxide-based substrates is all fine. But eventually, the primary motivation was to move towards silicon compatibility. So we decided to grow hafnia, HzO, and perhaps recreate the same phases that we saw, such as the rhombohedral phase that we saw, directly on silicon. And for that, we took advantage of, we took epitaxial growth of YSZ, the ETR stabilized zirconia on silicon, which is very well used in superconducting literature, high TC superconductors, where zirconia actually scavenges the native silicon oxide layer, forming through this reaction, and then that enables an epitaxial growth of HzO directly on silicon. So this is a very recent result. In fact, we do have well-textured films, which I'll be in a better position to present more results about these films next year, perhaps. Okay, so it is possible to grow these films epitaxially on silicon and try and reproduce these polar phases. So in conclusion, let me say that there is nanoscale robust ferroelectricity in hafnia zirconia alloys, and we discovered a new rhombohedral phase with large values of spontaneous polarization, and when you reduce the film thickness, the polarization values further increase. There is no wake-up, and a simple model that can explain all these observations is nanoparticle pressure immense gigapascals nanoparticle pressure plus a substrate compressive strain, and this seems to be general in other simple oxides also. And finally, HzO can be epitaxially grown on silicon directly without any buffering or whatever. I would like to thank the MSCA fellowship that funds this project for me at least, and then gives me money to travel across. And then here there is a logo of the conference, which also provides some travel support and all these funding agencies. Thank you. I take any questions.
We'll give a couple of minutes for questions.
Yeah, so thank you. That's very interesting. So you mentioned about a preprint or